In this screencast, we establish the expressions that we need to find the total kinetic energy for a rigid body. And we do that by starting with a multi-particle system and establishing the separation principle of kinetic energy. Now, we've said before that for a single particle, the kinetic energy is 1/2 multiplied times the mass of the particle multiplied times the dot product of the velocity of the particle as observed in the inertial reference frame with itself. And we can express it two different ways, as a dot product, but also as 1/2 multiplied times the mass multiplied times the norm of the velocity squared. And so taking this kinetic energy for a single particle, we can now expand that into the kinetic energy for a multi-particle system. So the total kinetic energy of a multi-particle system, we'll replace our subscripts instead of the P, it now becomes an I, and we add up the kinetic energy for every single particle. And we can write this in two different forms. So in any multi-particle system, we have a center of mass of the entire system. And so given this center of mass, we can separate our velocity vector in the inertial reference frame into a triad. And so this is the velocity of any particle I with respect to O as observed in the inertial reference frame is equal to the velocity of the center of mass, G, as observed in the inertial reference frame, plus the velocity of any particle with respect to the center of mass. And so by substituting this vector triad into expression for our total kinetic energy, we get a new expression for our total kinetic energy. And here we have the dot product of the portions of our vector triads. And then when we calculate this through, we end up with three terms in the expression where we have 1/2 the mass, total mass, multiplied by the velocity of g with respect to O, dotted with the velocity of g with respect to O, then 1/2 the mass multiplied times the dot product of the velocity of I with respect to g with each other, and then the term where we have our velocity of g with respect to O dotted with the velocity of I with respect to g. There's two of those terms, and so quickly we see that our 2's cancel out. But then let's reduce this expression even further. So let's examine this last expression more closely. The first thing we can do is we recognize that the velocity of g with respect to O isn't dependent upon this summation. So we take it out. So the velocity of g with respect to O, as observed in the inertial reference frame, is dotted with the sum of the mass multiplied times the velocity of I with respect to g. Now recall that we can take out the time differentiation of any of our vectors and switch the order of our sum. So we get that this is dotted with the time differentiation, as observed in the inertial reference frame, now of the summation from 1 to n of our position, of our mass multiplied times our position vector of r I with respect to g. And we also know that this summation of the mass of I mass and then the position vector of I with respect to g is equal to 0 due to our center of mass corollary, so our entire last term goes to 0. And then when we rewrite what's left in our simpler expression, we get 1/2 the mass of all the particles multiplied times the norm of the velocity of the center of mass with respect to inertially fixed point squared, plus 1/2, and then we have to keep this within the summation of the velocity of each individual particle squared multiplied times its mass. And so we can define this as the kinetic energy of g with respect to O plus the kinetic energy about point G, or about the center of mass. And so we see here that kinetic energy separates just like angular momentum, in which we have something about an inertially fixed point, or the center of mass with respect to an inertially fixed point, and then the kinetic energy about the center of mass. So let's take our expression for our total kinetic energy of any multi-particle system that's generic and apply our rigid body constraints to make this work for us. So first off, we see that our first term is going to be 1/2 the mass of the center of mass, or the total mass of the rigid body multiplied times the translational velocity of the center of mass squared. So we'll leave that term alone because it's simplified enough, but let's look at the last one. We have a well-defined definition of the velocity of any particle within a rigid body as observed in the inertial reference frame. And that's if we take the time derivative in the inertial reference frame of any position vector I with respect to g. And so to do that, we're going to apply the transport equation. So we'll take the time derivative within the body frame of the position vector I with respect to g and add to it omega b as observed in the inertial reference frame crossed with the position vector I with respect to g. And the position of I with respect to g as observed in the b frame will be equal to 0, so that leaves that our velocity of I with respect to g is only equal to omega cross r. So we substitute this into our expression for our kinetic energy about the center of mass. And so here we obtain this expression for the kinetic energy about the center of mass, where we've simply substituted omega cross r of I with respect to g into the expression. And then in plane motion, the angular velocity of b as observed in I will be a scalar in the b3 direction. And when we substitute this in, we see that we have a scalar that we can pull out, which is not dependent upon the summation. But then we're left with b3 crossed with the position vector. And then this expression reduces to only r of I with respect to g, because it's the scalar, and b3 has a scalar value of 1. And this finally leaves us with the expression of 1/2 multiplied times the angular velocity, or the angular speed squared, and then we have the summation of the mass for each individual particle multiplied times r of I with respect to g squared. And one more simplification that we have here is that we should recognize this as being the moment of inertia about the center of mass. And then in our final expressions, we see that we have 1/2 multiplied times the moment of inertia multiplied by the angular velocity of b with respect to I, the norm of this squared. And so now we have two very simple expressions that provide insight into the origins and the contributions that the motion of the rigid body makes toward the kinetic energy. We have the translational kinetic energy, which has the form that we're used to, which is 1/2 mv squared. And that's the velocity of the center of mass as observed in the inertial reference frame. And then we add to that the 1/2, and now instead of mass, it's now the moment of inertia about the center of mass, and then multiplied times omega squared, where omega is the angular velocity of b as observed in the inertial reference frame. And so we have a translational kinetic energy and then a rotational kinetic energy. Now it's very important here to point out that the velocity of the center of mass with respect to the inertial of the center of mass must be observed in the inertial reference frame, as well as the angular velocity of the rigid body must be observed in the inertial reference frame for this to be true.